This smell. Rotting seaweed. Marsh gas. That sulfurous stink at low tide. Dimethyl sulfide. DMS. On Earth, this molecule comes almost exclusively from life. Phytoplankton, bacteria, biology processing sulfur. And in 2023, the James Webb Space Telescope detected it. 124 light-years away, on a world 8 times Earth's mass, covered in water, wrapped in hydrogen. The announcement was careful, cautious. Possible biosignature. Then other scientists looked at the same data, and they didn't see it. This is the story of one of the most important claims in astronomy, and why, 2 years later, we still don't know if it's real. September 2023. The James Webb Space Telescope observes K2-18b, an exoplanet in the constellation Leo, 124 light-years from Earth. JWST doesn't photograph distant exoplanets. Instead, it uses spectroscopy. When K2-18b passes in front of its star, a transit, starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths, leave fingerprints. Water vapor, methane, carbon dioxide, all detected clearly. And then, something else. A faint absorption feature, matching dimethyl sulfide. The team, led by Niku Madhusudan at Cambridge, spent months analyzing the data, checking calibration, looking for instrumental artifacts. The signal was there. Weak, but there. 3 sigma confidence. In statistics, that means 99.7% confidence. Sounds good, right? In astronomy, 3 sigma means interesting, but not confirmed. There's a 1 in 370 chance it's just noise, a false alarm. For comparison, when CERN discovered the Higgs boson, they waited for 5 sigma. That's 1 in 3.5 million chance of error, the gold standard. The K2-18b team published their findings in September 2023. Carefully worded. Tentative detection. Possible biosignature. Requires confirmation. But before we get to the controversy that followed, we need to understand what kind of world could produce this signal. K2-18b is nothing like Earth. Mass 8.6 times Earth. Radius 2.6 times Earth. Gravity about twice Earth's surface gravity. It orbits a red dwarf, a star smaller and cooler than our Sun. Every 33 days, K2-18b completes one orbit. But here's what makes it special. K2-18b is what astronomers call a Hycean world. Hydrogen plus ocean equals Hycean. The structure from inside out. A rocky or icy core, then a global ocean, potentially hundreds of kilometers deep. Liquid water under immense pressure. And covering everything, a thick hydrogen-helium atmosphere, thousands of kilometers deep. It's like Jupiter's atmosphere sitting on top of Earth's ocean. A completely alien architecture. JWST's data suggests the right conditions exist. Temperatures between -73 degrees Celsius and +100 degrees Celsius, depending on depth and latitude. Pressure, allowing liquid water. Energy from the star. The planet sits in the habitable zone, not too close to its star, not too far. Could life exist there? The chemistry says maybe. Which brings us back to that smell.
On Earth, dimethyl sulfide has a very specific origin. Phytoplankton, microscopic algae, produce a compound called DMSP. It helps them regulate internal pressure, protects against stress. When phytoplankton die or are eaten, DMSP breaks down. One product, DMS. Every year, phytoplankton release about 28 million tons of DMS into Earth's atmosphere. In the air, DMS oxidizes, forms sulfate particles. Those particles seed clouds. More phytoplankton, more DMS, more clouds, cooler ocean temperatures. It's a climate regulation cycle, and it's entirely biological. We don't know of significant abiotic sources of DMS. No volcanoes produce it in large amounts. No atmospheric chemistry creates it without life. So if K2-18b has atmospheric DMS, is something alive there? The 2023 team didn't claim they'd found life. They said, "We detected a molecule that, on Earth, only biology produces in significant amounts. This warrants further investigation." And further investigation is exactly what happened, just not in the way they hoped. For nearly 2 years, the K2-18b DMS detection stood as an intriguing possibility. More James Webb Space Telescope observations were scheduled. Papers were written about Hycean biosignatures. Then July 2025 happened. A NASA-led team headed by Renyu Hu at JPL published their own analysis. Same JWST data, same spectroscopic observations. Their conclusion? No conclusive evidence for DMS. The NASA team used different atmospheric models, different analysis techniques, and when they processed the data their way, the DMS signal wasn't convincing. Cambridge team? 3 sigma detection, probably real. NASA team? Signal present but below confidence threshold, probably noise. How can 2 expert teams analyze the same data and reach opposite conclusions? The problem? K2-18b's atmosphere is crowded with molecules. Water vapor, methane, carbon dioxide. Each absorbs infrared light at multiple wavelengths. Those absorption features overlap, blend together. The DMS feature is weak, right next to stronger methane lines. Extracting it requires complex modeling of all the other molecules first. If your atmospheric model is slightly different assumptions about temperature profile, cloud coverage, mixing ratios, you extract a different signal. Cambridge's model assumes certain cloud properties, extracts DMS signal. NASA's model? Different cloud assumptions. DMS signal vanishes into noise. Both models are scientifically valid. Both teams are experts. And then a third team weighed in. August 2025. A third independent analysis, published in Astronomy and Astrophysics, led by researchers across multiple European institutions. No stake in either the Cambridge or NASA claims. Their verdict? Insufficient evidence for DMS or related sulfur compounds. But they provided something useful. Numbers. To definitively confirm or rule out DMS at K2-18b's abundance level, they calculated we'd need approximately 25 additional high-quality transit observations using JWST's MIRI instrument. MIRI can detect longer wavelengths than the NIRS-PEC instrument used in 2023. Better sensitivity for certain molecules. 25 transits. K2-18b transits every 33 days.
That's 2 years of observations if JWST watched every single transit. But JWST doesn't watch K2-18b exclusively. It has thousands of targets. Observation time is fiercely competitive. Realistic timeline? 3 to 5 years to accumulate enough data. We're talking 2028 to 2030 for a definitive answer. But here's where it gets more complicated. Because while astronomers were debating K2-18b, chemists made a discovery. In 2024, a team of chemists simulated exoplanet atmospheric conditions in the lab. High pressure, hydrogen-rich gas, UV radiation, sulfur compounds. They were testing whether DMS could form without life through pure chemistry. Result: yes, under certain conditions, abiotic DMS formation is possible. Not huge amounts, but detectable. The mechanism involves photochemical reactions, UV light breaking apart hydrogen sulfide and methane, then recombining into DMS. It requires specific conditions, but those conditions might exist in Hycean atmospheres. And there's more. Astronomers have now detected DMS in comets, in the interstellar medium, the gas between stars. The claim that only life produces DMS is no longer accurate. Abiotic DMS exists. We've found it. We've made it in labs. This doesn't mean K2-18b's potential DMS is abiotic, but it means we can't assume it's biological either. DMS went from strong biosignature to ambiguous signal in the span of 2 years. For biosignature hunters, this is a setback. But it's also progress. We're learning what does and doesn't indicate life. So where does that leave the K2-18b claim? Let's be clear. Nobody is lying. Nobody made errors. The disagreement isn't about competence. It's about interpretation. When you're detecting signals at the absolute edge of your instrument's capabilities, analysis choices matter enormously. How do you model clouds? Which baseline do you use for the continuum? How do you account for stellar variability? What statistical framework do you use? Every choice is defensible, but different choices lead to different results. It's like a magic eye picture. Some people see the 3D image instantly. Others see nothing but noise. Same image, different perception. Except here, we can't just relax our eyes and suddenly see clearly. This has happened before in astronomy. 1967, Jocelyn Bell discovers pulsars, rapidly pulsing radio sources. Initial hypothesis: LGM1. Little green men. Alien signals? Debate raged. Alternative theories proposed. More observations collected. Answer: rotating neutron stars. Natural phenomenon, not aliens. But the initial uncertainty was real. Multiple explanations fit the data until more data narrowed it down. We're in that uncertain phase with K2-18b, and the scientific community has split into 3 camps. Camp 1, the believers. Led by the original detection team, they stand by their analysis. Point out, the signal is consistent across multiple transits,
DMS, and potentially DMDS, dimethyl disulfide, another sulfur compound. Both appear. The methane to carbon dioxide ratio is unusual, suggesting disequilibrium chemistry. Abiotic DMS production might not reach observed levels. Their position. We've detected something real. It's probably DMS. And while abiotic production is now possible, biological production remains the simplest explanation. Camp 2, the Skeptics. Led by the NASA reanalysis team, they argue the signal is too weak to be conclusive. Alternative atmospheric models don't show DMS. Instrumental systematics could mimic the signature. Abiotic DMS production weakens the biosignature case. Extraordinary claims require extraordinary evidence. Their position. The data doesn't support a robust detection. We need much more evidence before claiming a biosignature. Camp 3, the wait and see. Majority. Most astronomers, they're watching the debate, but not taking strong positions. They say, both analyses have merit. 3 sigma is genuinely ambiguous. More data will resolve this. Getting excited prematurely risks another phosphine on Venus situation. That was the 2020 claim of phosphine, another biosignature gas in Venus's atmosphere. Made headlines, generated huge excitement, then fell apart under scrutiny. Signal was less certain than initially claimed. Alternative explanations emerged. The lesson: wait for 5 sigma. Don't overinterpret 3 sigma detections. Be patient. But patience is hard when the stakes are this high. If K2-18b has life, everything changes. The Drake equation estimates the number of technological civilizations in our galaxy. I'll spare you the actual equation, but what you need to know is that most variables are now constrained by observations. Star formation rate, known. Fraction with planets, approximately 1. Nearly all stars have planets. Habitable planets per star, approximately 0.1 to 1. But then we hit uncertainty. FL, fraction where life develops, unknown. This is the great unknown. Does life emerge readily when conditions allow? Or is Earth a 1 in a trillion fluke? If K2-18b has life, fraction where life develops is probably high, 0.1 to 1. Life is common when liquid water and energy exist. The galaxy could be teeming with biospheres. If K2-18b doesn't have life, or the signal is false, we learn nothing about FL. Keep searching. And here's why Hycean worlds matter. Mini-Neptunes are the most common type of exoplanet. If they can host life, we're not looking for Earth 2.0 anymore. We're looking at thousands of ocean worlds wrapped in hydrogen. Vastly more habitable real estate than rocky planets. But this makes the Fermi paradox worse. If life is common, intelligence might be too. Where are they? Why no signals? No megastructures? Maybe. Life is common, intelligence is rare. Intelligence is common, technology is rare. Technology is common, longevity is rare. They exist, but we're not seeing them. Or maybe K2-18b's signal is noise, and we're still alone in any detectable way. Which brings us to the hardest question. How do we decide? Here's what people think science is. Make observation. Formulate hypothesis. Test hypothesis. Get answer. Done. Here's what science actually is. Make observation. formulate multiple competing hypotheses, test with limited data, get ambiguous results, debate interpretation, collect more data, repeat for years or decades. K2-18b is science in real time. 2023. We detected something. 2024. We need more observations. 2025. Actually, we disagree on what you detected. This isn't broken science. This is normal science. The public wants binary answers. Is there life? Yes or no? Science deals in probabilities. Based on current evidence, we're X% confident that Bayesian reasoning. Start with prior probability, how likely before evidence. Update with evidence, what data shows. Get posterior probability, how likely after evidence. For K2-18b, prior probability of life, very low. We have 0 confirmed examples of life beyond Earth. Evidence strength, weak to moderate. 3 sigma detection, debated. Posterior probability, still low but slightly higher than before. To overcome that low prior, we need very strong evidence. 3 sigma isn't enough. 5 sigma might be. And getting to 5 sigma requires something precious. Time. JWST is the most oversubscribed telescope in history. For every hour of observation time available, there are 9 to 10 hours of proposals requesting it. 90% of proposals get rejected. Not because they're bad science, because there simply isn't enough time. K2-18b is competing with distant galaxies revealing cosmic dawn, exoplanet atmospheres on dozens of worlds, star formation regions, supernova remnants, black hole environments. All scientifically valuable, all deserving observation time. The committee deciding asks, is K2-18b's uncertain DMS detection worth 25 more transits? That's 50 to 75 hours of prime telescope time, when we could study 25 other exoplanets in that time. The answer? Partial yes. K2-18b has been allocated additional observation time for 2025 to 2026. Not 25 transits, maybe 5 to 8. Enough to push toward 4 sigma confidence. Not quite enough for 5 sigma. Realistic timeline, 2025 to 2026. Additional observations, approximately 4 sigma confidence. 2027 to 2028. If signal holds, more time allocated. 2028 to 2030. Possible 5 sigma confirmation or definitive refutation. 5 years. Maybe more. Unless something unexpected happens. JWST isn't the only telescope watching. Extremely Large Telescope, ELT, 39-meter mirror, under construction in Chile. First light expected late 2020s. Giant Magellan Telescope, GMT, 25-meter effective aperture, Chile, late 2020s. 30-meter telescope, TMT, 30-meter primary, Hawaii or Chile, site disputed. 2030s. These ground-based telescopes will have spectroscopic capabilities rivaling or exceeding JWST for some observations. They could provide independent confirmation or refutation. And beyond JWST, Habitable Worlds Observatory, NASA's planned successor, 2040s. Specifically designed to study potentially habitable exoplanets. LUVOIR/HabEx concepts.
Large UV/optical/infrared telescopes could directly image some exoplanets, not just use transit spectroscopy. Every decade, our capabilities improve dramatically. What takes JWST 25 transits to confirm might take the next generation 5 transits. And K2-18b isn't the only target. Hundreds of other Hycean candidates, rocky planets in habitable zones, Europa and Enceladus in our own solar system. If life is out there, we're building the tools to find it. The question is, what do we do while we wait? The search for life beyond Earth is older than modern astronomy. 16th century, Giordano Bruno speculates about infinite worlds with life. Early 1900s, Percival Lowell claims to see canals on Mars. Evidence of Martian civilization. Turns out, optical illusion. No canals, no Martians. 1976, Viking landers search for life on Mars. Ambiguous results. Debate for decades. Current consensus? Probably not life. Probably exotic chemistry. 1996. Possible fossilized bacteria in Martian meteorite. Huge announcement. Presidential statement. Current consensus? Probably not fossils. Probably mineral formations. We've been here before, multiple times. Every generation thinks it might be the one to discover life. Every time, the evidence falls short. But here's what's different now. Our tools are better. JWST can analyze atmospheric chemistry light years away. We have the technology to actually answer the question. And we're learning from mistakes. Demand 5 sigma before claiming discovery. Exhaust natural explanations first. Independent replication required. Honest about uncertainty. K2-18b is a test of our improved methodology. Can we remain skeptical while staying open-minded? Can we handle ambiguity without declaring premature victory or giving up? The answer matters for how we conduct the search going forward. Imagine it's 2029. After years of additional observations, multiple independent teams using different instruments agree. DMS is confirmed on K2-18b at 5 sigma confidence. What happens? First, we've detected a biosignature gas on an exoplanet. Not proof of life, biosignature, but the strongest hint we've ever had. Second, follow-up intensifies. Other biosignatures searched for: oxygen, methane disequilibrium, seasonal variations. Third, other Hycean worlds move to top priority for observation. Fourth, humanity processes what it means. We're not alone. Life arose twice independently. Abiogenesis isn't impossibly rare. The universe is probably full of life. But here's the bittersweet truth. 124 light-years away. Even at 10% light speed, far beyond our current capability, it would take 1,240 years to reach K2-18b. We'll never visit, never see its ocean, never meet whatever lives there. All we can do is watch, study light that takes 124 years to reach us. If we confirm life today, it existed in 1901. We're seeing the past. But knowing life exists elsewhere, that changes everything anyway. But there's another possibility.
Imagine instead it's 2029, and after years of observations, the signal hasn't strengthened. The DMS detection was a 3 sigma fluke. Instrumental noise. Overlapping spectral lines misinterpreted. What then? First, we learned about Hycean atmospheric chemistry, water vapor abundance, methane-CO2 ratios, cloud properties, temperature profiles. That knowledge improves our models for analyzing other worlds. Second, we refined our biosignature detection methods, learned what confidence level is truly needed, what pitfalls to avoid. Third, we practiced patience, resisted declaring victory prematurely, let the scientific process work. Fourth, we keep looking. K2-18b wasn't the one. Doesn't mean life doesn't exist elsewhere. Hundreds of other candidates. The search continues. Here's the statistical reality. If life is common in the galaxy, we'll probably find it within a few decades of serious searching. If life is rare, we might search for centuries and find nothing. The only way to know which is to keep searching. And that's exactly what we're doing. Right now, in November 2025, K2-18b exists in a superposition. Like Schrödinger's cat, simultaneously has life and doesn't have life. Until we open the box with more observations, the DMS is real and isn't real. Both possibilities exist. Every 33 days, K2-18b transits its star. Sometimes JWST watches, sometimes it doesn't, busy with other targets. Data accumulates slowly. Uncertainty shrinks gradually. 3 to 5 years, maybe more. Eventually we'll know. Either we confirm the first atmospheric biosignature beyond Earth, or we learn this wasn't it and keep searching. But here's what we already know for certain. We have the technology to detect life if it exists in detectable forms. We've found thousands of exoplanets, hundreds potentially habitable. The age-old question, are we alone, has moved from philosophy to empirical science. The answer is coming. Not today, not this year, but within our lifetimes. We've found the smell of life, 124 light-years away. Maybe. And maybe is the most important word in science. September 2023. For the first time, we detected a potential biosignature on an exoplanet, Dimethyl sulfide, on K2-18b, 124 light-years away. It was tantalizing. A molecule that, on Earth, comes almost exclusively from life, on a world with a global ocean beneath a hydrogen sky. Detected at 3 sigma confidence. Interesting, but not conclusive. Then other scientists looked at the same data, and the signal became uncertain. Was it real? Some say yes. Was it noise? Others say probably. Was it abiotic chemistry we don't understand? Maybe. 2 years later, we still don't know what we found. And that's okay. Science doesn't always provide immediate answers. Sometimes it provides better questions. The questions K2-18b left us. Can Hycean worlds host life? How do we distinguish biological from abiotic chemistry? What confidence level is truly needed before we claim a biosignature? How do we balance excitement with skepticism? More observations are coming. More Hycean worlds being studied. Better instruments being built. Maybe K2-18b's signal will strengthen, confirming the first atmospheric biosignature beyond Earth. Maybe the signal will fade, teaching us about exotic atmospheric chemistry instead.
maybe another world will show clearer signs, forcing us to reconsider what life looks like. K2-18b is still there, 124 light-years away, its ocean churning beneath hydrogen clouds. Whether life exists in those depths or not, we won't know for years. But we're asking the question the right way now, with telescopes, with data, with honest uncertainty. And eventually, 3 years, 5 years, a decade, the universe will answer. We found the smell of life. Maybe. And maybe is where all great discoveries begin. This is Cosmic Canvas, where we explore the universe's mysteries, even when those mysteries remain unsolved. Until next time, stay skeptical, stay curious, and keep watching the data. The answer is coming.